Hello, this is Fabio Traversa. I'm the CTO of Memcomputing, a spin-off from University of California, San Diego. During this call, I'm going to introduce a new computing paradigm we call Memcomputing as the company. But before introducing Memcomputing, let me just recall what is a Turing machine. That is a very simple, ideal concept of a computing machine that really describes all computers and computing architectures that we use today to perform tasks. And the Turing machine is a very simple concept, as I said, and it is composed of, it is an ideal object composed of a tape in which there are symbols that are written, and there is an head that can read and write those symbols following a table of instructions. Now, this is a very useful mathematical concept because we can use this to address the computational complexity of problems that we try to solve with our computers. And not only that, we can use also to optimize design of computing architectures. And talking about design of computer architectures, for example, most of them, if not all of them, basically have in common this very simple sketch of architecture, which we call today von Neumann architecture. And this is very simple. As I said, we have an input device that sends inputs to a central processing unit that computes these inputs. And while it is computing, since it cannot store really the memory itself, it exchanges continuously with a memory unit the data that is processing. And when it finishes to process, which means it finishes all the stages of an algorithm, then it outputs the results. Now, the first thing that here we can see is that there is a main limitation for this architecture, which is the bottleneck of exchanging constantly data between the memory unit and the processing unit. This is called the von Neumann bottleneck. And why it is a bottleneck? Not just because it creates a bottleneck in the speed, but also because the 90% of the energy expenditure for today's architectures comes from the data exchange between memory and processing units. So avoiding this step will be a great leap in computing architectures. And nevertheless, we have basically that all our modern computing architecture have this scheme. They follow this scheme, starting from GPU, CPU, ending to more specialized architectures like ASICs and FPGAs. However, they are very efficient in doing many tasks like graphics, machine learning, simulation, data analytics, and so forth. In fact, we use them every day, and we use them starting from our watches that today are smart watches, because they can perform many tasks like very small computers, and finishing to warehouse that contains humongous amount of data, and they continuously compute. And in fact, today, most of the computations is migrating to what is called, for example, the cloud computing. And in fact, people, they limited use cloud computing, but for example, larger enterprises, even governments are migrating their needs to cloud computing instead of in-house servers. And in fact, the need of computation is every day growing. Here, there is a forecast of how much energy we are going to need to continue the trend of our computation of today. And in fact, by 2030, 2035, these forecasts say that we will have not anymore enough energy just to run our servers. And that's not the only problem. There is another problem, that the trend of the Moore law is unfortunately finishing. The Moore law is a very simple law that says that basically you can double the number of transistors within a unit of area of a chip, of an integrated circuits. But unfortunately, we have arrived to about 7 nanometers, which is basically a physical limit, because with that channel length, we already are experiencing a lot of quantum effects in our transistors, which means that they don't really behave as we expect. And therefore, there is a big need for new computing architectures. For example, many large corporations are working on quantum computing, starting from IBM, finishing to Google, Microsoft, and Intel, just to mention some of the big players. Then there are also startups that are trying to build quantum computers. And then there is also this called neuromorphic computing, which is basically trying to mimic our brain and put the brain on a chip, essentially. So sort of neural network on chip. So they are asynchronous circuits that tries to perform some computation. That is still in its infancy, I will say, because they are a very hard circuit to manage. And finally, there is MEM computing, which is the proposal that we have done here at the University of California, which is a bit different. It's kind of resemble neuromorphic computing, but instead of having something that are basically spiking neural networks, we use instead a self-organizing circuit that try to manipulate algebra and logic. I will show you how. But however, before going to discuss how a Memcomputing machine work, let me just recall that those machines obviously from standard to unconventional computing can be used also to perform attacks to our secure systems today. And just let me briefly divide the attacks into two big families. One is brute force attacks. So, for example, breaking keys or inventing SHA-2 or recovering passwords. And the other attack, obviously, can be smarter, like exploiting vulnerability, credential stuffing, phishing, and so on. We will concentrate more here on brute force attack because we want to know what really new architectures can do in terms of computations. So we are not going to try to use them so smartly. And so here we can divide basically the cyber attacks into the smart ones that are basically the ones that we can do with our conventional hardware. And that's why we don't try even to do brute force attacks with conventional hardware, because they, for example, imagine RSA, and that is based on factorization of prime numbers, has been chosen the factorization exactly because it's a very difficult and intensive tasks for today's architecture. So those are problems that are, let's say, impossible to solve, to be solved by standard computing machine, computers, and so forth. Or at least they will need the age or the time that overcome the age of the universe. Then we have neuromorphic computing, as I said, and that unfortunately makes no promises about some attacks, so really is not geared towards these problems. Then we have quantum computing, which actually it became famous because Shor in the 90s showed that if you had a quantum computer, you can actually factorize large prime numbers. Obviously, you need a large quantum computer to do that. And then finally, there is MEM computing. Now, MEM computing has been devised not to make cyber attacks, but has been devised to solve hard combinatorial problems. And I will show how. And but obviously, if you can solve hard combinatorial problems, maybe you can solve hard SAT problems, which ultimately can be used to make cyber attacks. And but before going on application on quantum on MEM computing, let me just briefly give an overview of where we stand with quantum computing, because I'm sure that someone of you it's curious to know if really you can use a quantum computer in short term to perform some attack. And so yeah, quantum computers are really beautiful objects. They are very complicated. You need a physicist to run a quantum computer. Of course, they are meant not just to solve prime factorization problems, but they will be great to, for example, simulate other quantum systems. So you can basically simulate molecules and make drug discovery. And for example, if we had some large quantum computer, we could have find very quickly some med for the COVID in this moment, but still they are in their infancy, and so we have just very small creation of this, and in fact we have two types of quantum computers today. One is based on quantum annealing. There is, for example, very famous Dewey machine that implements quantum annealing. However, quantum annealing is not really what you expect from a typical quantum computer. Quantum annealing is more used to solve optimization problems, and really even today is not really well known how useful is going to be a quantum annealing machine. Then on the other side, we have another type of quantum computer, which is basically what is trying to build, or what is building IBM, for example, which is a system composed of several quantum bits, and they are fully entangled, and you can manipulate those using what they are called quantum gates. Now, is this kind of quantum computer, which is called also universal quantum computer, that you can use to implement the Shor algorithm. And for example, the IBM quantum computer, you can do that, but unfortunately, today you have just at your disposal like 10 or something like that fully entangled qubit. And just to give an order of magnitude of how many qubits you need to really break a 1024 bit key, you are going to need the order of 10 to the 6 order of millions of fully entangled qubit. And just to give an idea, in 10 years, maybe IBM will arrive to 100 fully entangled qubits if they are lucky, because the qubits really do not double every year like the transistors, because it's very hard to increase the number of fully entangled qubits in a system of qubits. So they rather add few qubits each year rather than multiplying the entire system. So let's say that using a quantum computer for attacks, it's still far away for now. And so now finally we have arrived to mem computing. That is this a new alternative we have introduced. So first of all, let me say, mem computing does not rely on a von Neumann architecture. And in fact, we introduced this as an idealization at the beginning of a computational memory itself. So let's see, so you can review a universal Memcomputing machine as a counterpart of a universal Turing machine. So it's a non-Turing type of computational paradigm. You have at the center, as I said, this computational memory, which is an ideal object, an ideal network of a small processor you can imagine that can store information and manipulate it at the same time without exchanging data with an external memory unit. Then you have this control unit that just sends signals in order to start the computation from the computational memory. Now, this as a mathematical object, it must have some extra feature we call, for example, we have defined this extra feature like intrinsic parallelism, which means that each of these processors will compute and perform computation all in parallel. Basically, you can imagine that there is sort of collective state of all these processors that drives their state in time. And then there is another important feature that they should have to really perform better than a Turing machine. They should be specialized. We call this information overhead, but basically means that this network must include some extra feature of the problem. So it's not just a random topology or something like a neural network, for example, that you train to have some property. We have formalized this concept. We have published a few peer-reviewed papers, and we have proved that if you have these, if you formalize this as you formalize, for example, a Turing machine, you discover that basically the Mem computing machine is equivalent to a non-deterministic Turing machine. This has a very immediate consequence, that is, you can solve with the Mem computing machine non-deterministic polynomial problems in polynomial time. Well, non-deterministic polynomial problem in polynomial time is a big claim, because it means that you can solve efficiently all satisfiability problems, for example. And for efficiently means in polynomial time. Now, anyway, that's the theory, right? So if you can build one of these machines, of course, you can, first of all, solve efficiently this hard computational complexity problem, and or mitigate the fundamental bottleneck, because again, I recall that these are basically computational memory. So the idea that was at the basis of this is that you eliminate the data exchange between processing unit and memory. And obviously, here is the challenge. That's all theory, but how we can design a practical Mem computing machine, so something that we can actually use to solve hard problems. And so we are working since roughly 2015 in designing Mem computing machines, and we have divided those in two big families. One that are self-organizing circuits, which we use to solve hard combinatorial problems, and another family that are based on dynamic computing random access memory architecture, that is, you can imagine really a RAM, but is composed of some cells that can communicate and can perform directly computation on the RAM without needing a CPU. I'm going to discuss today just the self-organizing circuit, because they are the ones that we can use to solve hard combinatorial problems. And therefore, you can imagine that one day you can use also to perform attacks with some of those machines. And so let me introduce a little bit more in detail what are the self-organizing circuit. Before doing that, let me just very briefly recall what is a Boolean gate. A Boolean gate is a very basic object, an input-output object, to be more precise. And in fact, we can feed inputs to the input terminals, and it will return an output at the output terminal, following what we call a truth table. This is, for example, the truth table of an AND gate. Now we can use this gate and put together with other similar gates form a Boolean circuit. We feed inputs. This will return outputs that we can use as new inputs for the next stage, and so forth, till arriving to the final output, that is the solution of whatever problem we are trying to solve with Boolean logic. Now, this is the sketch of how basically internally our computers really are working. Let us rethink about this so we can introduce one possible realization of a Mem computing machine. So let's consider again the same gate. This gate is an AND gate, but at this time we do not limit our gate to just being a sequential object, but we allow our gate to accept input and output from all terminals. So, and they are superpositional signals essentially, and the only requirement is that being a dynamical system, it will self-organize, it will, in order to satisfy the relation, in this case, the end relation. Here, self-organize, you can imagine, as I say, the dynamical system. Self-organize means that it will find an equilibrium if and only if the Boolean relation is satisfied. Otherwise, you can imagine that there are current voltages there until it is not satisfied. They will fluctuate in time. Now, we can take these self-organizing gates and form a self-organizing circuit. This is exactly one of those computational memories I was talking about. And in fact, we can use this to solve directly problems without exchanging data with a memory, an external memory. In fact, it's enough that we fix some of the nodes as inputs, and then when the entire circuit will self-organize, will rearrange voltages and currents, then we can read the output. Why this is solving a problem? Because imagine that if the circuit has found an equilibrium, it means that all gates involved are satisfied. So you can encode a problem into the gates that you want to be satisfied, and those will satisfy a Boolean relation, which means you are finding the solution to a satisfiability problem, just rearranging all voltages in a circuit. How they really work, how you can design something like this. As I said, they are basically electronic circuit. So let's consider this simple sketch here of a gate, and let's look inside. In this gate, we can see that there are these blocks, DCM, we call them dynamic correcting modules. How they work? Imagine that the configuration of the gate is the following, and this is an AND gate. This means that this configuration is not consistent with the AND relation, and in fact, either the upper right terminal should be 1 or the output terminal should be 0. Now, since the configuration is wrong, we have these dynamic correcting modules that what they do is feeding some current. For example, the upper dynamic correcting module will feed a current trying to raise the voltage at the upper terminal and switching from 0 to 1, while the bottom DCM will do exactly the opposite, trying to lower the voltage from 1 to 0. So they are working collectively here. You can imagine that all these dynamic correcting modules, they are all working together into the circuit, trying to satisfy all the gates at once. Now, can we really design those DCMs? Yes, we can. We have done several designs, patented them, and we are currently even building those things. And they are simple feedback circuits, feedback nonlinear circuits that they instantaneously can read the voltage state at the terminal, and they accordingly inject some current in order to behave as I explained before. How we use those, as I just said, we can take our problem, whatever it is, we can write down as a set of Boolean formulas, and then we build a circuit that resemble exactly, that embeds these Boolean formulas. So we are creating a self-organizing circuit that is specialized for that instant of the problem. Here we find, for example, what I was talking about, this information overhead. So each of those circuits is specialized for an instance of a problem, because the connectivity is a mapping of the problem itself into the circuit. Now, why this should work? I'm not going to bother you with a lot of math here. We have written many articles explaining all the properties that these circuits should have. We have used a lot of functional analysis, topology, topological field theory, and so forth. And in principle, you can have essentially a dynamical system. You can design a dynamical system that from wherever you make it start, it will converge to an equilibrium, and that equilibrium is essentially the solution of your problem. That's the overall concept. How you can do that is not super easy, because those are nonlinear dynamical systems, but it is possible. And that is what we are designing at Memcomputing and also at UC San Diego in this moment. Here, just to give some extra information of those circuits. They do not work really like a normal digital circuit in which you have your gates. They work like more like, as I said, like a dynamical system, and they in fact show some of the effects that you would find in a quantum computer. For example, there is an emergence of what are called scale-free correlation. It means that these circuits, they have all nodes, all gates that are extremely correlated, which means that if you perturb some point in the circuit, any other point very far from that point feels almost instantaneously the perturbation. This is kind of a non-local effect that we leverage to converge very quickly to the solution of the problems. Then there is also other effects, for example, a sort of classical tunneling that we find in these circuits that is very similar to what happens also in quantum computers, but this is completely classical. And we call this emergence of instantonic phases, which is basically the system jumps from saddle points to saddle points, reaching equilibria or saddle points that have lesser and lesser unstable directions, and finally reaching the global minimum of the circuit. How we use now this to solve finally some problem. Well, for example, here I'm going to comment how to use these new architectures to solve satisfiability problems. And let me recall that a satisfiability problem in conjunctive normal form is a collection of clauses, and each clause includes literals that are variables or negation of variables. And the goal here, if it's a general maximum satisfiability problems that includes also normal satisfiability problems, is maximizing, is finding an assignment to the variables that maximizes the number of clauses that are satisfied, and how we can use memcomputing to solve a system like this. So let's consider, for example, this conjunctive normal form and a Boolean circuit that represents this conjunctive normal form, as you see from this slide. So how it is representing: for each clause, there is a NOR gate, an n-terminal OR gate that exactly represent that clause. And then all inputs are connecting following the variables. Obviously, you can see that you cannot really use standard Boolean circuits to solve this problem. The reason is very simple, because the unknown of these problems are the voltages or the state of the input terminals of these OR gates. And so a standard OR gate cannot provide the inputs knowing the output. But if they are self-organizing gates, so if those are memcomputing gates, essentially, we can just feed once to the output, and so requiring that those gates are essentially satisfied, and all voltages at the terminal will rearrange, will self-organize in order to find an assignment that satisfies all these OR gates. Okay, so we have even tested this emulating in software. For example, these are some preliminary SAT we did with the Supercomputing Center of San Diego. We were solving here some hard SAT problems, and we were comparing from against one of the best solver from the SAT competition that was the DCLS. Is called. This is from 2016-17 are those tests here, and we can see that with Memcomputing the scaling is essentially linear in solving those problems, and we arrived to solve instances of those problems up to 64 million variables, which are very large circuit. They include for this kind of tests, they were including more than 300 million gates. So you can imagine, and we were simulating just this in software, the dynamics of this circuit. So they were pretty efficient in solving these instances of problems. And also, here just to show the simulation itself that does not require really big uses of memory and so forth. Even the RAM that we used to make the simulation of those circuits was really bounded, just proportional to the input size. And so that's, for example, how you can use Memcomputing to solve such problems. We have many more articles that are around that you can look on the internet that shows other tests. So, for example, on Ising problems that are the ones that you solve usually with quantum computers and other SAT instances. Just these days, there is another article from UCSD that Max Diventra tested Memcomputing to solve hard distance of instances of SAT problems on Scientific Report. Then just to give a broader overview of Memcomputing, let me also discuss how you can use it to solve not just satisfiability problems, but more general problems like integer linear programming problems. Now, integer linear programming problems, probably everybody knows how they are. They are basically a collection of linear inequalities, and you want to find assignments to the variables. That variables can be continuous, discrete, binary variables that satisfy all these inequalities, and plus you have usually an objective function which is linear that you want to either minimize or maximize. How we can solve these kind of problems using Memcomputing? And this is a little bit more complicated because we should design gates that are no longer logic gates. Those are a little bit more complicated because they are what we call self-organizing algebraic gates, and they are meant to solve this linear inequality. So for each of these algebraic gates, self-organizing algebraic gates, we associate one of the linear inequalities of the ILP problem. And so the entire circuit that is an interconnection of those gates will try to find an assignment to the variables that satisfy all constraints at once. And the idea here is very similar to self-organizing logic. And in fact, those gates are composed of dynamic corrective modules, and they do the same work. They will inject currents in order to change the state of the voltages according to the entire states of that gate. We have tested this on many problems. Actually, the implementation of self-organizing algebraic gates is the product of our company at the moment, and we are using to solve many other optimization problems that the industry is facing today. And unfortunately, I cannot really share what we are doing with industry because basically all the projects that we have are covered by NDA, but I can share some public tests that we have done that is out there. For example, there is a very famous library for people that deal with integer linear programming, which is called MIPLIB. This is the library that usually is used to test solvers. Now, there are a couple of articles that are out there that describe many tests that we have done or other people have done on the MIPLIB, but there is here just want to discuss in particular one problem, just to give you an idea, that is F2000. This problem actually is in in this library, but comes from the pseudo Boolean competition, and is essentially a SAT problem, okay, that is there, and it is very, very hard. It's been there 8 years. Nobody has been able to solve this problem, and we were using just to benchmark our first release of the solver. This is back in 2018, and here, for example, this is the old web page from the library that says that the feasibility is even unknown because nobody was able to find any solution to this problem. And we ran while we were benchmarking our system, and we find solution within 60 seconds, the first one, and then multiple solutions just running longer. And it was a great achievement for our first prototype of integer programming solver using Mem computing. And in fact, now on the website you can go, and it reports that we have solved this problem with. We've been the first that after 8 years were able to solve F2000. And also another application, recently Airbus proposed a series of 5 problems that they could not really solve efficiently, and they proposed a challenge for quantum computers, right? And what we did was picking one of them, just because we could not really participate to the challenge because it was for quantum computers and not for other technologies, even if we submitted our solution, but obviously they didn't accept for the reasons I just said. And one of these that we solved, and there is a paper out there that explains how to do, is the optimization of the aircraft loading. And so basically you have an aircraft, and you have to load several different containers with different sizes, and you have many different constraints here, starting from the total weight, total volume, and the shear curve, and the center of gravity, and so forth. So it's a pretty complicated problem. And we showed how to transform this problem into an ILP, and how to run with Mem computing. And here, for example, there is some test we did that shows how you find the global optimum of this problem at scale, scaling the size up to very large instances of the problem that is basically what they face today for the cargos. And as a final application that I'm gonna very briefly discuss today is the training of neural network. For example, we have applied to both supervised and unsupervised training, because those are essentially optimization problems, okay? Pretty hard to solve because they are non-convex and unconstrained optimization problems. And for example, here, just to briefly report what we did with a restricted Boltzmann machine. And so you have basically a restricted Boltzmann machine that is a multi-layer deep network, sorry, that is a multi-layer of restricted Boltzmann machines, all stacked. And this usually is very hard to train, and in fact you cannot just use directly normal gradient descent methods or similar, but you need to pre-train the machine before training it. And usually the way in which you pre-train it is using a method that is called contrastive divergence. Now that contrastive divergence is kind of efficient, but really not so much, in the sense that it takes many epochs to make a good pre-training. There is, for example, the contrastive divergence using Gibbs sampling that is the most used, and we can see that, for example, within 50 pre-training iterations, still our network is not trained. And then Lockheed Martin had this great idea of using a quantum annealer, D-Wave. They just bought D-Wave at the time when they did this test, and they showed that you can use quantum annealing in order to boost the pre-training. And how you do that, you basically replace the contrastive divergence with a quadratic unconstrained binary problem, and if you sample from this quantum computer while it's trying to solve this problem, you can have sampling to pre-train your restricted Boltzmann machine. And since we can do roughly the same with the Mem computing machine, so we can, because it's a circuit, you can implement this quadratic unconstrained binary problem on it, and since it solves with the dynamics of the circuit, you can basically do the same. You can sample from the very dynamics of the Mem computing circuit, which is what we did, and the results are what are reported here. So we were able to train at optimality the restricted Boltzmann machine, even slightly better than a quantum computer, just because it is affected by non-ideality, since it is a real hardware. And with this, I finish my talk, and thank you for listening. If you have any questions, please.
Meanwhile, Fabio joined us. So Fabio, if you can hear me, can you turn on your video?
Yes, sure. Hi.
Okay. Hi, thank you for the talk. And as I said before to the other speakers, there is a little bit of delay from the Zoom call to the YouTube stream. So we'll wait about 1 minute to see if there are questions. Meanwhile, there is, yes, there is one question from Emanuele that says, for quantum computing, there are libraries that you can use to start playing with the coding paradigm. Even though, of course, when you run your code, it's emulated on regular computers, is there any tool that we can use to start playing with mem computing?
Yes, sure. So as I said, we have a company in San Diego right now, and what we are developing at the moment is a simulator of these circuits. Is called Virtual Mem Computing Machine, just because we emulate and we are not really building it. We probably will start building some of those ones specific for some tasks starting next year. And you can go on our website and register for free, especially if you are either a university or you work with some company. We can provide access, free time that you can use to start playing with computing. Since we, as I said during the talk, we are using mostly for solving optimization problems from industry. You can plug problems in ILP format, not in SAT format. But that's really, if you have a SAT problem, transforming into an ILP is a trivial task. So you can actually even run after converting satisfiability problems on it. Again, that is an emulation of those circuits. So still is not as efficient as you would have if you build it. But definitely you can start playing and see how it reacts when you try to solve hard combinatorial problems like satisfiability ones.
Okay, thank you. So I see that there are no more questions. So oh, sorry. Yes, there is one question. What are the possible applications of Mem computing to cybersecurity?
Yes, as I discussed, since you can try to solve satisfiability problem, you can use to perform attacks, and so to see if I don't know, trying to factorize large numbers or even trying to attack hash system like SHA-2. SHA-2, at the end of the day, is a bunch of one-way functions. All of them are Boolean. And the idea is that you can, for example, build a circuit and try to just invert brute force SHA-2 rather than trying to find all combinations like they do, for example, for mining Bitcoins or crypto values. So yeah, the easy and straight answer is that you can use basically to try attacks to secure systems.
Okay, thank you. I have one last question that may be silly, but I'll try. And do you have compared your SAT solving tools with the common tools that are used in hacking or CTFs like Z3?
No, for many reasons. So the most important reason is that our commercial grade solution is more focused on optimization problems, because obviously, you know, we are a startup. We have tried to have some revenue, and making attacks. Yes, you can try to build a market around that, but really, if you have something that solves efficiently optimization problem, combinatorial problems, you can use for other more lucrative applications. Like, for example, we are working a lot with oil and gas or with transportation logistics. You can imagine that this field, they have many hard problems that they need to solve. And in fact, we are working with them. And that is the most trivial answer. The second reason why we are not doing that at the moment, because we really prefer working with governments about that, because, you know, if it is involved national security is something that we prefer having the government involved.